Welcome to this channel Chemistry Made Easy by Dr. Ashok Mulik. Today we will see our original topic, that is atomic structure, and today's point of interest is applications of Bohr's theory to multi-electron systems. So last time we have seen what is Bohr's model of an atom, specifically for hydrogen, because hydrogen is a single electron system. So initial investigations and the model was developed for hydrogen, and it was found that this model of hydrogen's atomic structure is well supported by the various concepts which are given in this Bohr's theory. So Bohr's theory is very well applicable to the hydrogen atom, that is single electron systems. But when it is applied to multi-electron systems, then it shows it cannot work most precisely. It sticks to the circular nature of orbits present around the nucleus. But this theory, this concept is not supported by various experimental investigations. That is, the experimental data obtained from spectroscopic methods does not found to be supporting the concepts proposed by this Bohr's theory for multi-electron systems, where the electrons are more than 2 or more. In case of such, we can have examples such as lithium, beryllium, boron, hydrogen, carbon, nitrogen, etc. So in such case, the theory cannot work properly. So the experimental investigations or data obtained from spectroscopic methods was compelling the theorist, that is the scientist, to work hard on this concept to explain the observations obtained from spectroscopic data. According to these observations, the various scientists proposed the spectral lines obtained in case of hydrogen. Now we will see how are these spectral lines obtained in case of hydrogen. So here we find that when n is equal to, when we consider the n is equal to 1, that is first orbit, that is first orbit, and energy level of this orbit is like this. Then if we consider the second orbit like this, n is equal to 2, the energy level of this n is equal to 2 orbit is like this. Then in case of n is equal to 3, the energy level is like this. Then when we consider n is equal to 4, the energy level is like this. Then when we consider n is equal to 5, the energy level is like this. In this way we can have n is equal to 6, where the energy level is much closer. Again, if we go for in this way, n is equal to infinity, the energy levels are like this. So we can have these various energy levels, but the final energy level is n is equal to infinity. Then the energies obtained according to Bohr's theory are like this. So E is equal to, for this, from the energy equation, Heisenberg constant for hydrogen, that is RH, into E1 upon n square L minus 1 upon n square H. So this equation gives the energy for hydrogen when n is equal to 1 is minus RH. In case of this, the energy is minus 1 upon 4 RH. This is for second energy level. Then for third energy level, the energy is minus 1 upon 9 RH. For n is equal to 4, it is minus 1 upon 16 RH. For n is equal to 5, it is minus 1 upon 25 RH. For n is equal to 6, it is minus 1 upon 36 RH. And for n is equal to infinity, it is 0. So, in this way, we can have the energies of these various energy levels. So, when the spectrum is obtained, in case of this hydrogen, what happens? The electron present at this n is equal to 1 jumps to higher energy levels depending upon the energy source available, that is h upon h nu, 1 h nu, 2 h nu, 3 h nu, etc. That is n h nu, we can see. Depending upon this, the energy will support or will be provided to this atom, because of which the electron present in this n is equal to 1 will jump to any other suitable higher energy level, and from this it will come back after losing the suitable amount of energy. So as a result of this, we can have the spectral lines. Say if the electron is jumping from second to 1, we get the spectral line in this way. From n is equal to 3, the electron can come to this energy. From n is equal to 4, the electron can come back to this level. From n is equal to 5, the electron comes back in this way. From n is equal to 6, the electron also comes back in this way. So this gives us the Lyman spectrum, Lyman series. So this Lyman series works well in case of UV region of spectrum. UV region of spectrum. Then we will show another type of series of the spectral lines. When n is equal to the electron from n is equal to 3 jumps back to this n is equal to 2. Again it jumps back from n is equal to 4. From n is equal to 5 and from n is equal to 6. In this way, we can get another spectral line. It is called Balmer series. So this works well in visible region of spectrum. Then, in case of third, that is, the electron can come back from this n is equal to 4 to n is equal to 3, n is equal to 5 to n is equal to 3, and n is equal to 6 to n is equal to 3. So this is called a Paschen series. Paschen series. So it works in IR region. So this works well in IR region. So hydrogen atom gives the spectral lines in this way. So first step of spectral lines are obtained that are named as Lyman series, which is obtained using the radiations from UV spectrum. And in case of Balmer series, the visible region is used here to obtain the spectral lines, and the transitions are taking place in this. From n is equal to 3 to 2, from 4 to 2, from 5 to 2, from 6 to 2. But here in case of Lyman, the transitions are taking place from 2 to 1, 3 to 1, 4 to 1, 5 to 1 and 6 to 1. In case of Paschen series, the transitions are taking place from n is equal to 4 to 3, 5 to 3, 6 to 3. So in this way, the different spectral lines are obtained. But here we find that the Bohr's theory shows that the data obtained is fitting to the hydrogen atomic model only, but it fails to work well in case of multi-electron systems. So it needs to consider an important characteristic of electron. It means why it does not work well for multi-electron system. So in order to understand, we have to consider that the electron should be working in different manner. It may not be like a particle, but it works in a different manner. So this makes compulsory for us to work to consider that the electron can work like a wave nature. It works as a wave nature. So electron works or behaves, we can say, behaves like a wave. Like a wave. Means it shows the properties of wave also. So this was obtained, or concept was made more clear by, or it can be described by the de Broglie's equation. De Broglie's equation in 1920s. So de Broglie gave its equation, that is lambda is equal to h upon 4 pi for h upon mv. We are considering another type of equation, that is h upon mv. Here we find that the lambda is wavelength, h is Planck's constant, m is mass of electron, and v is the velocity of the particle or wave, that is of electron. So these are the various terms used by de Broglie, and this de Broglie shows that the, or we can say it describes the wave nature and as well as particle nature of the electron. Means according to this equation we say the electron when moving in the orbit behaves like a wave. So moving, because electron is moving in the orbits and this movement is like a wave. So we can say that all moving particles have wave nature. Then electrons moving in circular orbit around the nucleus, as we have seen in the Bohr's theory, shows that, or it makes us to think that the electron forms the standing waves when it is moving in the circular orbit. But according to de Broglie's equation, it shows the properties of wave nature, that is the properties of wave, and this was considered in the form of Heisenberg's uncertainty principle. That the de Broglie's concept that is introduced in order to explain the wave nature plus the particle nature of the wave electron is also to be explained together, and this was explained by Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. What is this uncertainty principle? It shows that, or we can say it states that there is a relationship between the inherent uncertainties in the location and momentum of electron in the moving particle or in the moving electron. Means moving electron and moving particle is behaving in the same way here, but in case of electron it shows that, means this Heisenberg's uncertainty principle shows that there is the relationship between the uncertainties of both, that is the location of electron as well as the momentum of electron which is moving in the orbits. So these uncertainties are observed when we are considering that the electron is moving in, say, any direction, that is x direction. So this is given by the equation, that is delta x into delta px is equal to or greater than, that is h upon 4 pi. H upon 4 pi. Here the delta x, shows the deviation or the uncertainties in, it shows uncertainties in location of an electron. Where it is moving around the orbit, around the nucleus in a specific orbit. Then this delta px is the uncertainties in momentum of electron, moving electron, of a moving electron. So here h is Planck's constant, so that we know. So this product, that is delta x into delta px, means uncertainties observed in locating the electron around the nucleus and the uncertainties observed in the momentum of moving electron. So this product is equal to or greater than h upon 4 pi. Now if or when we observe the spectral lines in case of the multi-electron systems, then it is observed that the uncertainties arising or uncertainties observed in case of momentum of electron are very small. So the degree of uncertainties in case of this delta px, that is momentum, are very small. It means the momentum of such electron can be more precisely obtained. The momentum can be more precisely obtained or determined. But in case of these uncertainties, the delta x, that is uncertainty in location, is very large. It means it is difficult to locate electron or determine the exact position of electron around the nucleus. So what is this uncertainty indicate? It indicates that it is very difficult to point out or to detect or to define the exact position of electron around the nucleus in the specific orbit. But at the same time, it is very easy, or we can say it is more precise, to determine the momentum of electron, moving electron. And so this is more precise determination, where it is very difficult or it is not much precise. Means it is very uncertain to determine the location, but it is relatively more precise to determine the momentum of electron. So that is why it was suggested that the location of the electron means what we are considering that n is equal to, say, 1, 2, 3, etc. Means we are trying to concentrate on the principal quantum number, that is the exact orbit of the electron. But it is very difficult according to this principle, that is, it is not suitable or it is not possible to exactly point out the position of electron, whether it is in the specific orbit. Means instead of considering or concentrating on the orbits of electron, it is very convenient to consider the orbitals. So these are pointing out the orbits, but it is very easy or convenient to consider the orbitals. So orbitals are easy to determine the location of the electron and also the momentum of electron. So all these things make it clear that on each order we can say it is very difficult, or we can say in other words it is difficult to find or finding of an electron around the nucleus in the specific orbit is difficult, but it is suitable to consider the orbitals. And we are also defining that the orbitals are the region around the nucleus. Say this is the orbital. Say when we say this is the orbital. Say this is say 1s orbital. Then such orbital, and in case of 1s it is all orbit and orbital is same, but we are considering it as a orbital. So when we consider orbital, it is very suitable or convenient to determine the position of electron as well as momentum of electron because it is orbital. But it is very difficult to consider the exact location and momentum of electron when we consider the orbit. So this is the difference, and therefore we say that the probability of finding an electron in the space at a specified point, that is the electron density, can be calculated when we consider the orbital. But it is difficult to consider the electron density in such orbits. So this is what we understand or we can understood from this concept, that is for specifically for multi-electron systems. So we will stop here our discussion and we will go to the next point in the next lecture. Till then, goodbye. See you next time. So kindly press the bell icon and like button, subscribe to this channel, and you can put your comments in the comment box. So thank you very much.